Understanding quantum locomotion, paths in the quantum realm. Introduction to quantum locomotion. The intricate dance of particles within the subatomic world, often perplexing and counterintuitive, finds an elegant description in the concept of quantum locomotion. This fascinating area of physics delves into how particles move in the quantum realm, not through simple trajectories, but by integrating two of physics' most profound principles, the principle of least action and the sum over histories*, also famously known as the Feynman path integral. 2. The principle of least action. At its heart, the principle of least action * posits a remarkably fundamental idea: objects, when unimpeded, naturally follow the path that requires the least action. But what exactly is action? In physics, action is a specific physical quantity derived from a system's energy, momentum, distance, and time over a given path. Think of it as a measure of the cost, or effort, associated with a particular trajectory. Historically, this principle has been a cornerstone of classical mechanics, beautifully explaining everything from the parabolic flight of a thrown ball to the orbits of planets. However, recent advancements and deeper understanding of quantum phenomena have confirmed its profound validity and applicability even for quantum particles, demonstrating its universal elegance across different scales of the universe. 3. The sum over histories, Feynman path integral. In stark contrast, or so it might seem, stands the sum over histories *, a revolutionary formulation of quantum mechanics pioneered by Richard Feynman. This core concept dictates that to determine the probability of a particle transitioning from one point to another, one must consider every conceivable path it could have taken between those points, not just the most obvious or direct one. Each of these infinite possible paths, or histories, contributes to the overall probability amplitude of the particle's movement. This formulation powerfully highlights the inherently probabilistic and many-pathed nature of quantum reality, suggesting that a particle doesn't simply choose one path, but rather explores all possibilities simultaneously, with each possibility carrying a certain weight towards the final outcome. IV. The synthesis, quantum locomotion explained. The apparent tension between least action, a single, efficient path, and sum over histories, all possible paths, is precisely where the genius of quantum locomotion lies. The crucial connection becomes evident when we consider specific conditions. While the sum over histories indeed involves summing all possible paths a particle might take, the principle of least action identifies a particular, remarkably efficient path among them. This convergence is most pronounced in the classical limit. This limit applies to larger systems, or when Planck's constant, a fundamental quantum value, is considered infinitesimally small. Under these circumstances, the paths that contribute most significantly to the sum over histories are precisely those that adhere closely to the principle of least action. The contributions from other, less efficient paths tend to cancel each other out due to destructive interference, leaving the least action path as the dominant one. Therefore, quantum locomotion implies a profound insight. While quantum particles fundamentally explore all possible trajectories, they will effectively appear to follow the most efficient path dictated by the principle of least action under these specific circumstances, giving rise to the deterministic behavior we observe in the macroscopic world. V key takeaway. Quantum locomotion stands as a testament to the elegant interconnectedness of physics, brilliantly bridging the inherently probabilistic nature of quantum mechanics with the seemingly deterministic appearance of classical physics. It demonstrates how apparent efficiency and predictable trajectories in our everyday world can emerge from the underlying summation of an infinite array of quantum possibilities.